Hi everyone, today I am going to talk about something that sounds scary, time complexity. But I promise by the end of this class, you will see it's just common sense. Imagine you are making pizza. The recipe has steps: knead dough, add sauce, cheese, and bake. If you make one pizza, you do those steps once. But if you make 100 of pizzas, you repeat the same steps 100 times. So the time grows with the number of pizzas, right? So in computing, algorithms are like recipes. They take input like the number of pizzas, and the time they take usually depends on how big that input is. So time complexity is just a way to describe how the running time grows as the input gets bigger. We do not care about exact seconds here. We care about the trend. So the time complexity is equals growth of operations with the input size n. Let's look at two really simple tasks. Now, if I ask you to add up all the numbers from 1 to n, how many addition do you do? For n equals to 10, you do 9 addition. But for n equals to 100, you do 99 additions. The number of operations is roughly n. So we say this is linear. It grows like a straight line. So this linearity, we define it as a order of n. So here the operations are proportional to n. Let's take another example, a multiplication table. Suppose you want to print a multiplication table of size n into n. So for n equals to 3, you print 3 into 3 equals 9 numbers, right? But for n equals to 10, you print 100 of numbers. So here the number of print operation is n square. So we call this quadratic, and it grows much faster, and we define it as a order of n square where the operations are proportional to n square. So complexity is about how fast the line goes up when you increase n. Now when you talk about growth, we often want to say things like, in the worst case, it wouldn't take more than, in the best case, it will take at least this, or in the average case, it is about this. That's where the big O and the big omega and big theta come in. They are like speed limit signs for algorithms. So this is big O and this is big omega, and this notation called the big theta. So let's start with the most famous one, the big O. Big O keeps an upper bound. It says no matter what, the time will not exceed this much. So if we take pizza delivery as a real life example, suppose you order a pizza, the restaurant says it will be delivered in the 30 minutes or less. If traffic is horrible, it wouldn't take more than 30 minutes. It is an upper bound. So big O is like that guarantee, at most this many steps. So the big O is an upper bound and worst case and the at most point. Suppose you have a list of n number of names and you are looking for a specific name. So the best case will be the name is the first one, you find it immediately, and at worst case it's the last one and you check all n names. So the worst case is n checks, and we say linear search is order of n. It will never take more than n steps. So order of n is a linear search. Let's take another example. Suppose you have two nested loops that both go up to n. The inner loop runs n times for each outer loop, so the total will be the n equals to n will be n square. That's order of n square. Even if you break early sometimes, the worst case is always n square. So now the big omega is the opposite. It gives a lower bound. It says it will take at least this much even in the best case. Suppose you are making a cup of tea and you have to boil water. Boiling takes at least 2 minutes, even if everything else is instant. So the lower bound is 2 minutes. That's omega of 1. It's a constant time. So what does big omega mean? So the big omega mean it's a lower bound. It is the best case. And it tells at least. Let's take the example of linear search again. If you were lucky and the name is the first element, you find it in one check. So the best case is constant time. So we write omega of 1. Notice here, one algorithm can have different upper and lower bounds. Linear search is order of n and omega of 1 is the best case. So now if we talk about the big theta, this is when the upper bound and the lower bound are the same. The algorithm's time grows exactly like that function for large inputs. Suppose you take a train that always takes exactly 30 minutes, no matter what. Then your travel time is big omega of 30 minutes. So it is both at least and at most 30 minutes. So this big theta means it's a tight bound, or you can say it a average case. And when upper and the lower match. Suppose you have an array of n numbers and you add them up. You must look at every element exactly once. So you do exactly n operations. No faster, no slower. So that's the big theta of n. Let's take another example. Suppose if you have two nested loops that always run n times each, and it's exactly n square operations. So the big theta will be the theta of n square. Let's recap what we have learned today. So number 1, the time complexity. So time complexity describes how the number of operations grows with input size. And our second one is the big O notation. So big O is the upper bound. It is for the worst case and the at most case. And number 3 is the big omega. It is the lower bound and it is used for the best case and the at least case. And the number 4 is the big theta. It is for the tight bound or the average case, and it points exactly to that growth. So this is the core idea. In the future classes, we will learn how to calculate these for different algorithms.